Hello friends, I am Snehal and I am teaching you physics. With this lecture, we are starting a course on 12th standard physics or second year of high school physics. And these are the topics which we are going to cover in this course. So we will start with electromagnetism. In electromagnetism, we will study electrostatics, then electricity, then magnetic effect of electric current, magnetism, electromagnetic induction and alternating current. Then the electromagnetic waves. So these are the topics which we will study in electromagnetism. After we study electromagnetism, we will move on to the study of optics, that is study of light. So in optics, we will study ray optics and wave optics. After we are done with optics, we'll move on to the modern physics, and in modern physics we'll study dual nature of light and matter, atoms, nuclei, semiconductors and communication systems. So these are the topics which we will cover in the course. In today's lecture, we'll start with the electrostatics, and in particular we'll start with electric charges and fields. So let us begin with some experimental observation. So let me erase this. Okay, so let us see observation number 1. Suppose we have two glass rods and we rub both of them on wool or silk. Then we try to bring them close to each other, and what happens is there is repulsion between these glass rods. Similarly, if we have plastic rods, these are plastic rods, we rub them with some animal fur, maybe cat or something, then we try to bring them close to each other and they also repel each other. So this is observation number 1. Observation number 2 is, if we take one glass rod which is rubbed with wool and one plastic rod which is rubbed with animal fur, we bring them close to each other, then they attract each other. So this is observation number 2. Let us see another observation. So this is a rigid support, this is nylon thread, and a metal ball is hung to this rigid support. Now suppose we bring this glass rod close to the metal ball. So this is a glass rod. So initially there is attraction between the glass rod and the metal ball. When we bring glass rod close to metal ball, once we touch it to the metal ball and remove, then there is repulsion between the glass rod and metal ball. So what is happening here? How do we understand these observations? So answer is, when we rub bodies onto each other, charges are developed on bodies. And why charges are developed? Answer to that is, everything is made up of atoms. We know atoms have this nucleus which is positively charged due to this protons. There are neutrons too, and surrounding that nucleus there are electrons. So this is the electron cloud and number of electrons. Then every substance is either made up of atoms or molecules, which in turn are made up of atoms. So when we rub bodies onto each other, the electrons from one body which has less electron affinity are transferred to the another body which has more electron affinity, and that's why one body loses negative charge and one body gains the negative charge. So the bodies become positively and negatively charged. So the charges on these glass rods are positive because they lose electrons, and charges on plastic rods rubbed with animal fur are negative because they gain electrons. And we should also know this fact that like charges repel each other and unlike charges attract each other. So when we try these two glass rods which are positively charged, we take them close to each other, there is repulsion because there are like charges, same type of charges on both the glass rods. Similarly, when we bring likely charged plastic rods close to each other, they also repel. But when we take this glass rod and plastic rod close to each other, they are unlikely charged, that's why they attract each other. But what about this case? Here we have this glass rod which is positively charged, but the metal ball does not have any charge. So what happens is, inside metals there are huge number of electrons, free electrons, which move in random directions. So when we bring this glass rod close to the metal ball, those electrons are attracted by the glass rod and they get accumulated on this side. So the other side has lack of electrons and therefore some positive charge is developed on the other side. Because these electrons are close, or the negative charge is close to glass rod compared to the positive charge, attraction dominates the repulsion between positive charges, and that's why initially there is attraction. But when we touch the metal ball with the glass rod, what happens is the metal ball has same amount of positive and negative charge, so it is uncharged, and glass rod has positive charge. So when we touch those two, there is redistribution of charges and some positive charge is developed on metal ball also. So when we remove the rod now and bring it close to metal ball again, now there is repulsion because now a metal ball also has positive charges and the glass rod, it also has positive charge. So this is how we understand these things. Now in this case we charged these bodies by rubbing onto each other. So this is charging by rubbing. This thing is, we charged metal ball by keeping this glass rod which was charged in contact with the metal ball. So this case is charging by contact. There is another way of charging which is called as charging by induction. We'll see that now. Now suppose we have this metal rod. Think whether it is possible to charge this metal rod by rubbing it on wool or silk. So answer is definitely no. And reason is, metals are conductors of electricity That means they allow charges to pass through them, and because of that, when we rub metal ball on animal fur, it will get negatively charged. But instantly what happens is the charges flow through the metal ball to our hand, to our body, and through our body they enter earth. So it gets uncharged again quickly. But if we use some insulating handle, so this is insulating handle, maybe glass, plastic or something, then, and suppose we take care that our hand does not come in contact with metal rod, we hold the handle only and do the experiment, rub the metal rod with wool or animal fur, then it will get charged. Then we can do these experiments. So there are two types of substances. Substances which allow charges to flow through them, they are called as conductors, and substances which do not allow charges to flow through them, they are called as insulators. Okay. Now let us see charging by induction. So we have these two metal balls kept in contact with each other, and as explained just now, we have to have these insulating stands. So these are insulating stands, and now suppose we bring this glass rod which is positively charged close to one of these metal balls. Now what will happen? The electrons through these metal balls, they will get attracted towards the glass rod, and some negative charge will get developed on this side. And because the other side will lack electrons, some positive charge will be developed on that other side. Now we hold these stands and carefully separate those two balls from each other slowly. Then what will happen, that this metal ball will have these electrons only, and there will be redistribution of electrons like this, and this metal ball has lack of electrons, so positive charge is developed on that metal ball. Notice that we did not touch any of the metal balls, and still these negative and positive charges are developed onto the metal balls. So this method of charging the materials is called as charging by induction. Now think whether it is possible to charge only one metal ball by induction, and answer is yes. So let us see how we charge one metal ball. So let me erase this. Suppose we have only one metal ball, and now we bring a plastic rod. So this is plastic rod rubbed with animal fur. We take it close to this metal ball. So now the electrons inside this metal ball will be repelled by this negatively charged plastic rod, and they will gather on this side, and because this side has lack of electrons, there will be positive charge developed on this side. Now we have to take out this negative charge by some mechanism. So we connect a wire to this side and we connect that wire to the ground. So this is grounding. Now these electrons will flow to the ground through this wire, and then there will be only this positive charge left, which is held there by the force of attraction due to this plastic rod. Then we remove this grounding, so only positive charge is left on this ball. Now if we remove this plastic rod, charges will be redistributed and there will be uniform distribution of this positive charge. So this is how we charge single metal ball by using the method of induction. So this is charging by induction. Okay, now let us see some properties of charges. So properties of charges. First one is that charges are quantized, or charge is quantized. Second one is charges add like scalars. And third property is charge is conserved. Locally. Now let us see them one by one. So first property is charge is quantized. And what does it mean is that the minimum amount of charge we can obtain anywhere, we can observe, is fixed, and it is equal to this number E, which is 1.6 into 10 raised to minus 19 coulombs. So this is the minimum charge one can observe anywhere in the universe. We cannot have charge less than this. This is charge on electron, it is negative, and the same is the magnitude of charge on proton, it is positive. Now suppose we have any body which has some charge. Let's say the charge is equal to Q, then that Q has to be equal to some integer multiplied by E. So Q will be equal to integral multiple of E. That means Q divided by E will be some integer. And reason is obvious, because we cannot have the charge less than this number, so charges are transferred to the bodies in multiple of this number only, in integer multiples. Therefore, whatever charge we'll have on any body, it will be just integer multiple of this number. So this is the meaning of this statement, that charge is quantized. Anyways, let's see the property number 2, the charges add like scalars. So suppose we have some body and there are n number of charges, Q1, Q2, Q3 up to Qn. So one may ask, what is total charge inside that body. So this property is quite obvious, or it is self-explanatory. The total charge will be just algebraic sum of all the charges present inside the body. So charges have magnitude, no directions, so that's why they act like scalars. Okay, and the next property is charge is conserved locally. So this word locally is very important. So we are not interested in such kind of condition that an electron disappears from here and it appears somewhere on the moon. So charge is still conserved, but there is no local conservation of charge. Now remember, when we rub glass rod on wool, what happens is there is redistribution of charge from one body to another body. No charge is created, no charge is destroyed. If we take the system of the glass rod and wool as an isolated system, then the total charge in that isolated system is conserved locally. Okay, now we can have reactions such as this. A neutron gets converted to proton and an electron. So proton has some charge plus E and electron has charge minus E. Now one may think that these charges are created out of nothing, but we have to take into account the total charge before this nuclear reaction and after the nuclear reaction. So total charge then and there is 0. So before the reaction, charge on neutron is 0. If we add the charges on proton and electron, the total charge is still 0. So this is the meaning of charges, or charge is conserved locally. So these are some properties of charges. Now let's put the things quantitatively. Okay, now let us see a rule which allows us to calculate exact amount of force between charges, and it is called as Coulomb's law after its inventor. So let us see Coulomb's law. So suppose we have two charges, Q1 and Q2, and R be the distance between two charges. So this is R. Now Coulomb says that the magnitude of force between these charges, force may be attractive or repulsive, but the magnitude F is directly proportional to the product of magnitude of charges, and F is inversely proportional to the square of distance between the two charges. So F is proportional to Q1, Q2, and F is inversely proportional to R square. So it follows inverse square law just like gravity. Let us combine these two equations. So we can write F is proportional to Q1, Q2 divided by R squared. And if we remove this proportionality sign and put equality sign, then we'll need a constant, we'll call it K. So F equals to K times Q1, Q2 divided by R squared. So this is Coulomb's law. Now we know the value of this K experimentally. So K is equal to 9 multiplied by 10 raised to 9, and the unit is Newton meter squared divided by Coulomb squared. As you can check, we can write K as Fr squared divided by Q1 Q2. So K equals to Fr squared upon Q1 Q2. Now the unit of K should be equal to unit of RHS. So force is measured in newtons, distance in meters, SI units. Charges have SI unit of Coulomb. So Coulomb times Coulomb is Coulomb squared. So what does it mean for us is that suppose we have two charges, Q1 and Q2, separated by 1 meter, and the magnitude of the charges is equal to 1 Coulomb and 1 Coulomb respectively. So two charges of 1 Coulomb each, separated by a distance of 1 meter. What will be force of attraction or repulsion between them? So force will be equal to 9 multiplied by 10 raised to 9 newtons. As you can see very easily that Q1 is 1, Q2 is 1 and R is 1. So this thing is equal to 1. So F is equal to K in magnitude, which is 9 times 10 raised to 9 newtons. Okay, now we can write this force in more suggestive form like this. F equals to 1 divided by 4 pi epsilon naught into Q1 Q2 upon R squared. Now why this form is more suggestive, I will tell you in later lectures. So here we have written K equals to this thing, 1 divided by 4 pi epsilon naught. So K equals to 1 divided by 4 pi epsilon naught. So we have this new constant here, which is epsilon naught, and we call it permittivity of free space. So this is one way to write Coulomb's force. Okay, but this is only magnitude of force, and force is vector quantity. So how to write this Coulomb's force vectorically? Let's see that. Vector notation or vector form. So suppose again we have these charges Q1 and Q2, and suppose this is x-axis, this is y-axis, this is r1 bar, the position vector of this charge Q1, this is r2 bar, the position vector of this charge Q2, and this is the line joining the two charges, and let's call this vector r12 bar. So it is directed from Q1 towards Q2, r12. Okay, and by triangle law it should be clear that r2 bar is equal to r1 bar plus r12 bar. So r12 bar equals to r2 bar minus r1 bar. Okay, now let's write force on Q2 due to Q1. So force on Q2 due to Q1 will denote this force by F21. So this is force on Q2 due to Q1. It is equal to K into Q1 Q2 divided by R squared. So we have written magnitude here. So R will be equal to magnitude of this R12 bar and let's put this suffix r12 here. Now we need to have some direction here because force is a vector, and on left hand side we have used vector notation. So the direction will be on 2 due to 1, so it will be in direction of r12 bar. Okay, and we have used this unit vector denoting that. So this is how we write force on Q2 due to Q1. Now whether this force will be attractive or repulsive, the sign of charges will take care of that. So suppose the charges are positive, or the product of the charges is positive. So this factor is positive. It means that the F bar will be some multiple of this vector r12. So it will be directed in this direction r12. It means that the force will be repulsive because it is force on 2 and due to 1, and it is directed in this direction r12 bar. So Q1 is pushing Q2 away from it. Okay, so force will be repulsive. And similarly, suppose product of two charges is negative, that means one of the two charge is negative, then we will have negative sign from this factor. So force will be some number multiplied by minus of r12 cap. So it will be in opposite direction of this r12. So force will be in this direction towards Q1, and it is force on Q2 due to Q1. Force is towards Q1, so Q1 is pulling Q2 towards it. Okay, so this is how we find direction, or whether the force is attractive or the force is repulsive. Now using Newton's third law, we can write force on 1 Q1 due to Q2, and this force will denote by F12. This is on 1 due to 2, and it will be equal to K into Q1 Q2 divided by R12 squared. This is the magnitude, so it doesn't matter where we have suffix 1 2 or 2 1 here, but we have to get this unit vector right. Now it is force on 1 due to 2, so it is force on 1 due to 2. It will be in direction from 2 towards 1. Okay, so it is unit vector will be from 2 towards 1. An easy way to memorize this is that force on 1 due to 2, we write it like this, F12. Whatever suffix we have here, the opposite to that suffix will have here. So suffix will be flipped over. So if we have 1 2 here, we will have 2 1 here. If we have 2 1 here, we will have 1 2 here. Okay, so this will be force on Q1 due to Q2. So this is how we write Coulomb's law in vector form. Now we have seen a lot of new things in this lecture. Please revise them. In next lecture, we will start at this point the Coulomb's law, and we will introduce the concept of electric fields. Thanks for watching the lecture.